So where we are is we're looking at theories of everything. We're looking at the attempt to unify all of physics and astronomy into one simple theory that pieces everything together. And we've looked through string theory, and we played some string theory movies a few months ago.
You can borrow this.
Yeah, you can borrow it because they're really good.
Figure out what is going on there.
I don't have a
No.
DVD player anymore.
Oh,
You can play it in your computer.
yeah.
No, I don't have a slot.
Oh, wow.
Laptop. My husband may have one of his.
Okay.
I have an Apple, one of those Apples.
Or we
Right.
can put it on a thumb drive because we also
We could, yeah.
rip them on.
Right back. And I think you can probably go to pbs.org and you can stream it.
Oh, you can stream it.
Yeah, I think they have it all
What's
freely.
the title of it?
It's a Nova movie. It's called The Elegant Universe.
The Elegant Universe by Brian Greene.
There's pencils.
We got time, so we're fine.
I got a pen from here. No.
You need some paper?
No, I brought my own paper.
Okay.
Okay.
Lawyers are always organized.
And then he's got a sequel too, and that is it The Nature of Space? No,
Well, as long as it's
Fabric of Reality.
fabric of reality.
Yeah, so Brian Greene, Greene,
Yeah, with an E at the end.
yeah, and it's The Elegant Universe and Fabric of the Cosmos. And they're both highly produced, fantastic looking, well-paced, good, consistent level videos. So.
They're hard to fathom.
Yeah, it is. I mean, the whole concept is. And we're going to play around with some of this hardness today. We are about 2.5 years into this, and we're getting close to the end of the first time through the astronomy. We'll either start over if there's interest, or we'll go in a different area. We'll just see what people do. Right now, it's hard to get people out here, but we'll see. So then we went on to another approach to a theory of everything involving information. So we went from string theory, where reality is made up of these little vibrating strings down at a fantastically small size of 10 to the minus 34th or 10 to the minus 35 meters, that their vibration, the number of wiggles in these little strings of higher dimensional stuff, determine what you have. If you have an electron, or if you have a quark, or yeah, fundamental particles. Then you've got the fundamental particles like quarks that then go on to make up protons and your larger composite particles, and then those make more composite particles like atoms, and then atoms make molecules, and you build up from there from a sort of reductionist view. Then we worked in information, saying that ones and zeros do a better job making a description of reality. And we played through how information and entropy are two sides of a coin. That a way to look at, are you familiar with what entropy is? Okay, that's it. That's good, all right. Entropy is really important. It comes out of thermodynamics originally, but now it's kind of snuck into lots of other. Yeah, it's the tendency over time for things to run down, become more disorganized. Thermodynamically, like in a car engine, you can never have 100% efficiency when the engine's running. You're burning up gas, and there's always heat that's going to come out of the engine block. There's always heat pouring out the tailpipe that you can't use to run the car. So that necessary loss of energy is entropy. But it's linked to lots of other things, and we kind of went through these. I'll just go through them real quick. We got these different ideas of information entropy. This is, we played with information being, when you look at special relativity, you see a rapidly moving pole the speed of the pole makes an outside observer see it as shortening. It's the Lorentz contraction. So going up at 0.9% the speed, 90% the speed of light, 0.9 c, you'll see a 20-meter pole look like it's under 9 meters and like it could fit inside of a barn. If you're riding on the pole, you're looking at the barn coming towards you, you see a barn that's 10 meters wide appear like it's less than 4.5 meters in size. So can the pole fit inside or not? It all depends on your point of view. It all depends on the information you have available to you. And that's just special relativity. That's Einstein's first contribution. Yeah. Then we looked at in the quantum realm, so the two big pillars of physics are relativity and quantum mechanics. They don't get along together, and that's the thing that keeps physicists up at night. But information is important here, in that when you beam light at a single slit, you expect one big blob of light. And if you put two slits in there, you might expect the overlapping light to create one nice spot on the back wall, maybe some dimmer sections over here. But when you do it in reality, go through one slit, you get the one spot. But when you go through the two slits, you get an interference pattern, as if the light is made of waves, which it is. If you imagine light only being a particle, little photons, then you would expect this kind of pattern. And what you see is this instead, that it's made of waves, which is great until you stick a little sensor on one of these to say, did the light go through this slit or not? And if you do make an observation there, if you get information about it, it snaps into a particle-like pattern. So getting information or making an observation changes reality. It's very bizarre. It's not what we expect. It's not what we see in our day-to-day life. I know. But this is a basic physics lab that they'll do in undergraduate college. And it gets even weirder. There's something called the quantum eraser effect, that if you make your observation, which would destroy the pattern, just give you this nice blur of light, but then you destroy your observation before the light gets to the screen, the pattern comes back. And this has been repeated many times in laboratories. It's a very hard experiment to do because light travels very quickly, but it still happens. Have you ever heard of Schrodinger's cat?
What?
Have you ever heard of Schrodinger's cat?
No.
Okay, Schrodinger was a quantum physicist who didn't like the weirdness going on here, and so he came up with this thought experiment of a kitty cat in a box.
I heard this just a few weeks ago, but I don't know with respect to what.
Okay, great. Well, you're going to get it right now.
I heard little dead cat box.
Yeah. And there's a lot of little memes out there of cats in boxes and stuff. So, but you set up this experiment like this. You've got a cat in the box, and you have this can of poison. I don't know what Schrodinger had against cats. And the can of poison gets triggered by a Geiger counter. And the Geiger counter is watching a lump of uranium over here. So whether the uranium breaks apart and releases some radioactive elements or not is a quantum event. So it's something down in the subatomic world that's going on here. And that's what then extends this quantum weirdness all the way up to something the size of a kitty cat. And so you set it up that if this sees a particle of radiation come off, the can goes off and horrible things happen. So you close the box. Now you know that this has a 50-50 chance of giving its particle off in the correct direction in, say, an hour. Without being able to observe it, without being able to see inside the box, then this observation isn't being made. So over time, you can't know whether the cat is still alive or not. The cat becomes, by percentage, more likely alive than dead, and later about 50-50 alive and dead, and then later more likely dead than alive as the hours go by. You're going to give them oxygen, of course. And so this is a process called entanglement, that you're connecting different parts of an experiment or a system more broadly with this quantum probability. Now, what does a 50% alive cat look like? I mean, that's craziness. It doesn't make sense at all. And that's what Schrodinger is trying to point out. And of course, once you open the lid, you know, yes or no. There are two big areas of thought in quantum physics to explain what's happening when you lift the lid up. And this book actually goes into great detail, and I'll talk about that. This is my ad hoc discussion we're getting to, is what physically is happening. What is the reality of this situation? Obviously, when you lift the lid, you're going to have a live or dead cat. The first and most commonly adopted viewpoint comes from a single meeting. I don't remember if it happened in Copenhagen or if it just got the name Copenhagen. But it's called the Copenhagen Interpretation because it kind of congealed out of this meeting. And that says that, yeah, the cat is partly some percent dead and some percent alive until someone observes it.
At least a possibility.
Right. The cat, I'll explain this way. When we look down at the subatomic world, we don't see solid particles. Electrons and atoms and things that make them up aren't little billiard balls moving around. They are waves of probability, basically. It's where the peak is bigger in the middle of the wave, the particles most likely found there, if you observe right now. Out near the tails, like a bell distribution where the students get an A and the F, are out here on the tails, the particles are less likely to be seen if I make an observation right now. So what you're doing is you're taking that wave nature of reality and extending it all the way up to a cat. You're making a cat smear out, or decohere is the technical term, into less likely alive and some probability alive and dead on this kind of bell curve. That's a weird way to think. I mean, that's not the world we see, but the Copenhagen Interpretation says that when I open it up, that wave of probability collapses, just instantaneously pops down to an answer. Now the cat's dead, now the cat's alive when I observe it. What makes your head ache is that, as I said 2 months ago, that if Bill, the grad student, goes in to open up the thing, because you don't want to get the researchers, the PhD people, exposed to poison gas or the trauma of seeing a dead cat. Just before Bill opens up the lid, you slam the door on Bill. Okay, now Bill, from your point of view, becomes entangled with the cat. You don't know whether Bill has seen a dead cat or a live cat. So now Bill has a 50% chance of seeing a dead cat or 50% chance of seeing a live cat. And so the weirdness can keep going. So then you reach for the door to do it, and then someone slams the live door out in the hallway, and they don't know you, and so now you've become entangled with Bill, with the cat, with the uranium. And so you kind of build up into this bizarro world. This is your taxpayer. Yeah. So, let's see, do I have a slide there? No. Do I have it? I thought I did. No, we'll get there. So that's the Copenhagen Interpretation, and it just kind of makes your head ache. Einstein didn't like this. He figured there had to be some hidden physics going on that explains what's going on, that this collapse idea just isn't the whole story. He even commented once saying, okay, well, if everybody stops looking at the moon, does it decohere, does it go away until someone looks at it? Which, you know, in a way, that's kind of what the Copenhagen interpretation does. The other big view, and the one that's proffered by this book, because it's called Something Deeply Hidden by Sean Carroll. This just came out a few weeks ago. I pre-ordered it back in April, and I'm chewing it up right now. The other one is called the Everett Many Worlds interpretation. And what Everett says is that, all right, so everything in the subatomic world's got this wave nature. And if you have a molecule, then it's a whole bunch of waves overlapping. In fact, that wave function really describes everything. In the same way that this is the cat alive or dead can extend through Bill and through me and onward, it extends all the way up to the universe's size. So actually there's one wave function that describes the whole universe. And that's it. And so it never changes, it doesn't collapse, there is no observational boop like that. What happens is every time an observation is made, all the other possible universes or possible ways the thing could have come out, live or dead cat, split, and the other universe goes away where you can't get to it anymore. It's just as real as you, but it just splits away. So every subatomic decision throughout the entire universe is constantly bifurcating whole copies of the universe away from us. The many worlds is the name of that.
That's why string theory makes sense. That's why string theory makes sense up until the point that you have to prove it.
Right. Yeah.
Look at it.
Yes. But the Everett's approach to this way of looking at reality is simpler. You don't have to add this collapse. You don't have to add new mathematics. The wave function describes everything in one big snap. Not Thanos' snap, but just one big snap. And he goes through, I'm about 2/3 of the way through the book, but he goes through explaining how this really simplifies everything and doesn't add all these other problems. So cat alive and dead, yeah, there's a universe where the cat's alive, universe where the cat's dead. You're just writing down one. And that's what you saw when you observed. So nothing unusual happened with you having to look at it just then. That seems to be a lot of universes. And that is an intuitive problem that bugs people. But they can do the calculation of how many universes you need space for up to this point in the universe, and it's not an infinite number. It's a very large number. It's 10 to the 10 to the 122 power. That's a fantastically massive number, but it's definitely not infinity. And the name for that is Hilbert Space. Mathematician Hilbert came up with a way to describe as many dimensions as you want and can use. So dimensions can be up, down, right, left, time. Could also be hot or cold, temperature. It could be whether I'm turning to this direction or that way. Those are two dimensions I could be doing. I could be hopping or not hopping. That's another dimension. So everything you can use to describe what's going on right now pops a new dimension of measurement out. And so everything that a subatomic particle can do in a moment describes another dimension of it. Big, big number, but still finite. So information again in the Copenhagen way of looking at it, the information defines what happens. It makes a collapse. In the Everett approach, it just bifurcates the universe and you go down on one branch or the other. don't think I'm going to just try to stick to the main ideas here.
Hard to summarize this.
Yeah, it is.
So deep.
It is deep. But the thing I was going to hit on, it was a question from last time, was talking about black holes and information and entropy. And one day, a mathematician was playing with the idea of memory stored in a little container, like a USB stick, and said, what's the maximum amount of information I can get crammed into a given spot? And the equations, when you work it out, actually describe a black hole. So a black hole is the maximum amount of information or material that you can cram into a given volume, period. And that volume is defined by the event horizon around it. The event horizon is the sphere around it of no return. So as you're heading into the black hole, gravity is increasing, and suddenly you get to a point where to get away from it, you have to go faster than the speed of light. So the point that the escape velocity reaches the speed of light, you're never going to get away from the black hole. It's bad news. But that shell that around that volume of space also defines the maximum amount of information. And the equation that describes that surface area of a black hole turns out to be the entropy of the black hole. So entropy pops back in, the maximum amount of information I can get into this memory stick black hole. That's not a very good memory stick because you can never get your presentation back, is the entropy. And the entropy is at a maximum for that part of space. So, really weird connection. Why does the universe work this way? But we don't know. Now the question that came up last time was, it's general relativity that describes how a black hole works. It talks about space and time curving so severely that light can't get back out. Also says that time comes to a stop at this surface. And do I have that? Where's that slide? There we go. Time itself is related to entropy. So all the other branches of physics, quantum mechanics and general relativity and special relativity, don't care about time. You can put a negative sign on the little t and the physics works just fine. So what makes the past past and the future future? Or in a black hole, what makes time come to a stop here and while it's flowing out here? Well, the linking seems to be entropy. And who was it here that asked about the linking between the two?
Mark?
I think it might have been Mark. Yeah. Saying how does these two things link? And I think I'm going to get to it later in this book. That's why I'll have an addendum next month. But it seems to be that as long as entropy can increase, then time keeps flowing. Once you've hit the maximum, then time stops. Once you've curved space as far as you can, time stops. So these two worlds do link through entropy. Quantum mechanics and information theory and general relativity do meet in this extreme environment. With the Everett many-world interpretation, there's another way to look at this. And that is that the decisions in the universe, the splitting off of new universes every time something happens, define the direction of time. That you only get splitting forward in time, you don't get them ever coming back together. That's just, universes don't re-merge. So this lack of a re-merging in the future gives us a direction. We know, remember the past, we only guess about the future. And that gives us a forward direction. So in the very, 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 very distant future, when everything is expanded and you have one little photon per megaparsec in space, and all the stars are gone, all of atoms and particles have fallen apart quantum mechanically and just given up to light, time will stop again. So there won't be anything more that can run down. The universe, as said, will have said to have died a heat death, because heat is entropy going out your tailpipe. So the very, very, very future of the universe is out the tailpipe. So entropy wins. And black holes themselves will even evaporate. They will go away via the process of Hawking radiation. So it's one of Stephen Hawking's big contributions, saying the question was, what happens to information that falls into a black hole? Is it gone from the universe? And that's a very serious problem. If you can destroy information, then yeah, the laws of quantum mechanics are really wrong. And physicists are scrambling to come up with a new thing, or they're out of a job. And so what we know is empty space is teeming with what are called little virtual particles. It actually helps build space itself. The interaction of things like when I put my hands together, what's really pushing together are shields of electrons that surround all my atoms. And they're negatively charged, so are the others, and like charges repel, so the atoms don't go through each other. But what's happening as I clap and rub my hands is that they are exchanging virtual photons. That's the force carrying charge of the electron. And so they're going real fast, and they're saying, hey, there's electrons real close by, and this communication of information is what keeps my hands from being able to go through, or me from falling through the table. So empty space is filled with these little particles that pop into existence, particle and its antiparticle. And as long as they re-meet and annihilate each other before anybody can observe them, the world just goes fine. And that's what we see happening. We can even do an experiment in the lab where we take two plates and we put them very, 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 very close together in a vacuum. And as we get really, really close, a little pressure appears to push them together. What's happening is in empty space, these little virtual particles are coming apart in every direction they want. But as you squish down the empty space, they lose the ability to go in the direction of the plates. The only place that they can now appear and reconnect are in the empty gap direction between the plates. Without that little push, the virtual particles on the outside are just bouncing away at the outside of the plates, pushing together. It's called the Casimir effect. No fabric is involved. But we can see that in a pretty simple lab experiment. So you can imagine near a black hole, these things are happening in empty space as well. But right there, very close to the point of no return, when they form, one of the pair gets sucked into the black hole and the other one just gets out. It's a very tiny little zone of this where the one particle is just able to escape. I mean, it takes a long time to get up out of the gravitational well of a black hole, but it gets away. The other particle doesn't. So this becomes a particle in the real world now, rather than being a virtual particle that annihilates. This becomes a negative particle that takes away energy from the black hole. So this looks like a temperature when you're sitting back and looking at a black hole. It's a very, 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 very cold temperature. It's like 0.0000001 Celsius, very close to absolute zero, but it is a temperature, which means black holes even will eventually evaporate. And that also answers the question, does the information get out? Yes, it does get out. Theoretically, a future super intelligent, mega technologically advanced civilization could come to a black hole that we throw a green couch into and reconstruct the green couch in the future by watching a black hole over 10 to the 200 years slowly evaporate. I don't want to wait that long to watch a green couch come back out, but theoretically you could. So we have this dance between information and entropy going on like crazy. So the question was, how does general relativity and time stopping relate to just the entropy we see every day? And that's the best I can point out right now, that the two do get married this way. Okay, so another important part of this is entropy itself and the arrow of time, is that for entropy to push us forward in time, the beginning of the universe had to be something really special. Now we already have, just looking at galaxies spreading apart throughout the universe, a picture that if you run the clock backwards, everything crowds back together into a tiny little point. And we call that the Big Bang. I think the name was actually a disparaging name to try to mock it when the theory came out, but it stuck. So this little point in the beginning where everything is all compressed down is very special. It's a very low entropy state. Because entropy, another way to think of it is, how hard is it to describe something? So like an egg. It's got a nice little shell, you got egg white, you got a yolk in the middle. If I tell you to picture an egg, you and I are all seeing an egg in our heads right now. So simple, low entropy idea. If I smash it and say, okay, now imagine a smashed egg on the floor. We're all going to have a different picture, because how far did the shell go? How much did the stuff splatter? That's a higher entropy state. It's more complex. There's more information needed to describe a smashed egg than just a normal egg. So the early universe, all being crushed down to a point, is simple to describe. It's got a very tiny volume, or maybe a point. It's got a temperature, volume, pressure maybe. There's not much you need. There's not many numbers you have to write down to describe the point right after the Big Bang. Later comes microwave TVs and computers and things like that. So time and entropy and information are all dancing around each other. So this equation for entropy kind of seems to be our next approach to a theory of everything. It's not what they're looking at when they're trying to figure out how all the forces and particles work out, but this low entropy beginning of the Big Bang helps give us a direction of time. It's also the point where you just had maybe one universe in the very beginning, and then a decision quantum mechanically was made to go yes universe, no universe, and then another decision was made as these particles started to do it. It's the beginning of the bifurcation in Everett's many world model. And away go the galaxies and stars, they expand away from each other, black holes eventually evaporate, and then you're left with a very, very empty universe again. So a very special beginning. All right. So what's interesting is that same idea, that Hilbert space that we need for the Everett's many worlds way of looking at universe, that same number, 10 to the 10 to the 122, shows up if you just look at our universe here. This is what's called the Hubble Bubble. With the universe expanding, there is a horizon around us beyond which galaxies and stars are expanding away from us so quickly that we'll never get any information about them. It's actually bigger than our current universe. The Big Bang's after effects glow, called the cosmic microwave background radiation, is there. We can use microwave telescopes and map it, and we're working at that very hard. Beyond that is this bubble of you'll never see it again, which is very similar to a black hole. There's another horizon beyond which you can never get information. And in the black hole, except for the very slow Hawking radiation, you can't right now go get whatever you want inside of a black hole. It's inaccessible to you. So if you take that bubble and say, all right, there's all sorts of different ways I can fill my universe bubble. I can make it completely empty. I can put one electron in it. I can fill it completely with electrons and everything in between. I can fill it completely with protons, completely with neutrons, half electrons, half neutrons. I can play with all the mathematical combinations of a little bit of stuff, mostly empty space, a little more stuff, a little less empty space, and blah, blah, blah. I make all these additional bubbles around us with every possible combination, and eventually I run out of combinations. There are no more ways to fill this bubble of universe with stuff. And eventually, someplace out here, 10 to the 10 to the 122 meters away, it has to repeat. You just, mathematically, there's no more combinations you can do. So we're doing this exactly like we are right now, someplace way out in the universe. So it's another way of looking at Hilbert space. It's another way to look at the Everett many world approach, is that, well, every combination happens. It's all splitting away and forming universes. In a universe that's nearly infinite in size, the same phenomenon is going to occur. So it gives you a little more support that Everett might be doing it right. So, well, another big link we have between these theories came from Jacob Birkenstein, saying that the maximum amount of information you can get into the black hole, I said it earlier, but just to emphasize it, it's the surface area of the black hole. It's not the volume. So if I want to put as much information in encyclopedias in this room as I can, you just fill the room with encyclopedias. That's because we live in a big clumsy world around us. But when you're really pushing physics to the maximum of information is actually stored on the sphere around and not the volume. And volume doesn't matter. I know, it doesn't make sense either. It's very, very counterintuitive. But that's the way a hologram works. You get a piece of film, you hit it with light, and you see a three-dimensional image. All the information you need to reconstruct a three-dimensional object image is in that little piece of film. So this is called the holographic principle. And if you look at the Hubble bubble, it's big enough for that. Now, is that where the information is stored, or is it a higher dimensional thing? Don't know. But we do know that it solves a lot of physics problems. I think I have a graphic for that. I guess I don't. That if you're trying to figure out some of the physics of a black hole, if you treat it in one dimension different, in the holographic way, you can do the math better. Or some problems that are difficult in that, if you switch back into a three-dimensional way, the problems work very well there. So you have a link now between quantum physics and general relativity that we didn't have before. Still an area of active research. This is still being worked on. This only came out in 2000, I think. So it's a very young theory. So the universe sort of acts like a computer in this way. It's kind of like the Matrix, like we're in a simulation, where information running on the surface of a computational something that's generating this illusion of a three-dimensional world made up of a wave function. That's sort of the mind-boggling weirdness. And the thing that makes the clock tick forward in this seeming simulation is entropy. All right, so that was a recap. And this is where we stopped last time, is another approach to trying to understand what's going on at the subatomic world. This is called loop quantum gravity, and where string theory monkeyed around with 11 dimensions and curled up spaces and stuff you'll see in the shows if you stream those shows. This sticks to just 3 dimensions of space and 1 of time. Something that loop quantum gravity does that string theory doesn't is it does create both space and time as part of the theory. They get created too. String theory just kind of assumes you have space as a backdrop, and that, even though that's the big kahuna right now in research, people admit that is a bit of a problem. That your theory doesn't really create everything that is there that you can label. This theory does not allow a singularity. So singularity is this idea that in the middle of the black hole, ultimately everything is crushed down to a single point. Or in the Big Bang, everything came from a single point. That's a problem because you start getting infinities. If you're going to say, what's the volume of a point? Well, it's 50 over 0. Like, makes my head hurt. And so it gives a limiting volume of how much you can compress stuff, which solves a lot of good problems like that. It is more intuitive, yes. So what we have here is a concept of like a network with various weights on connections. And how these networks, these are mathematical networks. It's not really something built out of strings or webs in the subatomic world. These are connections that then construct space and time and energy and the flow of information through these. So you get, as connections are made and changed, you get the passage of time, you get particles and energy that move and transform. You play with concepts of these loops intersecting with mathematical planes and how they interact and the strength of them. Gives you a different field-like effect of gravity or electromagnetism, strong or weak nuclear forces, and may even give a solution to how the universe superinflated right after the Big Bang occurred. May help us figure out what this acceleration force that we see that was discovered in '98 called dark energy. So again, brand new discovery. Everyone's still chewing on the facts that the universe is accelerating its expansion. It's not just expanding. So the more you compress fabric of space-time, the more these loops have to compress. And the smallest space you can get is that same Planck size, this 10 to the minus 35 meters that is the realm of the little strings in string theory is also the realm of the smallest thing that you can get in this theory. And the reason that 10 to the minus 35 meters is a floor in size is that as I try to observe something, I need to use more energy to look at it as it gets smaller. So if I want to look at a mountain or a thunderstorm, I can use radio waves. That's what radar is. And so I can beam these big, tens of meter long waves of electromagnetic radiation out and bounce it off a mountain and come back and I get a picture on my computer of the mountain or the thunderstorm. But if I want to observe a table with radar, the wave is bigger than this room. And so I'm going to get a very fuzzy idea that there's a table. So I need to switch to light. So visible light is a much more energetic, much shorter wavelength. That's great, but let's say I want to look at an atom in the table. Well, light is not going to do it. Light will go right around the atom. And so I need to switch to something more energetic, like X-rays, and get up to wavelengths that high. If I want to go even further below the atom, then I've got to go up to gamma ray radiation and theoretically higher. When you get down to 10 to the minus 35 meters, you're trying to mathematically try to observe something that small, then the wavelength, energy level of that wave, it makes the photon pop into a black hole for a moment. So you're not going to get it, it evaporates immediately, but you're not going to be able to get any measurements smaller than that. So it's an ultimate smallness, or the true idea of an atom in Greek thinking, when they came up with the word, was that the smallest indivisible point or something that makes up something. And they never imagined actually seeing atoms like we do today, or that atoms would be made of smaller particles and those parts would be made of smaller particles. But this really is a limit. That is the bottom. And the time it takes light to go across that distance is 10 to the minus 44 seconds. So light goes across that little teeny space. That's our smallest tick of time in the universe. And so the reason that you can't go all the way down to some single singularity in loop quantum gravity is that you've got these little gaps in space in which there isn't anything definable in less than minus 10 to 35 meters. And so if you try to get a wave scrunched down in there, you're going to get the points where the wave actually intersects with the reality are these little stars right here. You're going to get a longer wavelength. So you just can't go lower. So you no longer have singularities. You don't have to divide by zero. The theories don't blow up in the same way. So that's kind of nice. That solves some serious problems. And you're not introducing tons of additional dimensions that are hard to envision. But it does make you wonder whether, as the universe before us, maybe there was one, maybe it collapsed in a way that we don't understand, because we don't think our universe is going to collapse, and it got down to a minimum size and bounced back out to form our universe. So what looks like our Big Bang is just the post-maximum compression time of some earlier version of the universe. And best we can tell, no information is going to survive through this. It's going to hit maximum entropy, maximum scrambling, so you're not going to be able to get a message in a bottle from the civilizations that came in the previous universe left to us, but we don't know. So it gives us the possibility that the Big Bang is a bounce, and it's just one that we'll have to continue to work on.
It's a clean, fresh start because there isn't any information.
As best we can tell, yeah. Now, maybe not. We have observed that most of the universe is made of matter, and that the early universe had an unequal amount of matter and antimatter created. By the standard model, that's difficult to have this imbalance. And so why is there a little bit more matter than antimatter? You know, when matter and antimatter meet, you just get pure gamma ray radiation, you just get pure light coming out of it. So why that little imbalance? Maybe that is a signature left over from the previous universe's conditions.
Otherwise you couldn't have extension.
Right. Yeah. So in the middle of a black hole, instead of a point in the middle, you get a maximum compressed space-time looping network, and it just waits until the day that it can evaporate. So maybe there's some kind of solid inside of a black hole, some compressed version of space and time. And Hawking radiation lets that eventually leak back out. All right, do I need to get into this? John Wheeler's thing.
Okay.
Yeah, that's a nice big number. We're just talking about I've already kind of covered that. This is just more examples of yes or no in information. And just for fun, I say if you have 10,000 coins piled up in the center of a room, then you start flipping them. What are the number of possibilities you can get out of just 10,000 coins? It's 2 to the 10,000 because there's 2 sides to each coin. And you can calculate that out. So the ways that these coins can be arranged is pretty fantastic, but it's not infinite. And if I were to flip 2 coins, like that one and that one, maybe just swap them, and you walk in a minute later and look, you wouldn't be able to tell the difference. So indistinguishable versions of these coin flips count the same. They don't count towards information gained or lost, which is related to the black hole surface. So looking really close at a black hole, these little Planck areas, either 0 or 1s all across them, and you say, well, I can flip one, flip another one, but the expression of how many flips of these coins I can do over the surface of a black hole is the expression of the entropy of the black hole. So, old and new definitions of entropy. It's the amount of hidden information or indistinguishable states. I can flip 2 coins, nobody knows the difference, so it's indistinguishable of a system. Or it's the information you can't recover. So, it could be the amount of energy a system has no longer available to do work. So the energy going out the tailpipe of the car is not going to make your car go any faster. And it's also the numerical measure of the uncertainty of an outcome. So whether the cat's alive or not gives you that forward direction in time. Going back to Maladicea, he's playing with the holographic universe idea, and that Hubble bubble, that bubble around us, that seems to be the information surface that we need for everything inside of our universe. And so his link at about year 2000 was to look at string theory as the volume and particle theory as the surface area. And like I said, the physics of both can be really nasty, but if you switch from the string theory over to particle theory or surface to volume, you can solve problems that you otherwise don't have the mathematics for. So he really linked these two. So a black hole here can be calculated in the way you would deal with hot radiation on just the surface. Or superstrings on the inside may look like fields if you do it, the calculations on the surface. So there's something here. There's something really fundamental that we're getting the taste of, that loop quantum gravity versus string theory may just be different expressions of the very same theory, just in how you deal with it holographically.
And it is all mathematics.
It's all mathematics, right? And that's why if you watch the video Elegant Universe, the elegant word is very specifically chosen to describe the mathematics. That they're really beautiful. That rather than just being crazy and random or unsolvable, things do become solvable and things do become simple.
In math.
In math.
Is math real or is it real?
Well, that goes to another philosophical question. Do we invent things mathematically, or do we discover things mathematically? And people love to bat that around. You have a beer around the fire at the campsite and discuss that. I think, gut feeling, most people feel that it is things to be discovered, because pure mathematics, just explored for the fun of exploring mathematics a century back, often find a use in the real world later. Like the equation to describe the strong nuclear force was just a mathematical game. And the guy working on that stumbled across it researching old mathematics books and papers and found that. The mathematics that help string theory work come from a mental exercise taking, you know what a Mobius strip is? Okay, you take a strip of paper, it's two-dimensional piece of paper, just a piece of ribbon, give it one twist and connect it. Okay, now weird things have happened. You have curved this two-dimensional piece of paper into the third dimension. And with the twist, you only have one side. Because if you start drawing all the way around, you go around a second time, oh, you're right back to where you started. You've drawn on both sides of the paper. So Mobius strip is kind of neat. By using the third dimension, you turn a second dimensional object into something with a one-dimensional line drawn on it. So you've just expanded your game across 3 dimensions. So they said, what if you had a 5-dimensional piece of paper and you give it a twist in the 6th dimension and you get a 4th dimensional surface drawn around it? What's the math for that? That's the same thing as 4, 5, and 6, or 9, 10, 11. Calabi Yar, 2 mathematicians, did that work. Here you go, world. And then string theorists went, oh my gosh, that's exactly what we needed to make our stuff work. So in the same way we talked about earlier, something called Mtheory showed that 5 different versions of string theory are really one. Maladicia's holographic theory kind of brings all the other theories potentially together as well. So string theory and quantum mechanics might just be different sides of a coin as well. Ultimately, we have to test all this. All this is great theory. There seems to be all these tantalizing connections. But one of the tests we need to do is, all right, does space really come in 10 to the minus 35 meter chunks? And does time really click along at that tiny little tick point or not? Is space smooth or choppy? Let's take a 10-minute break and rest our brains, and we'll get into that. Yeah, that's your brain. Yes. Well, you jumped right in at the culmination of a lot of stuff. I'm going to mute. Well, that's obviously on. That's good. Test, test. Okay.
On we go.
So the question is, you know, we can't get down to 10 to the minus 35 meters. We can't probe that directly. We can't even get close, even with CERN. In fact, the thought is it a moth? The thought is that, you know, you could make significant progress into the subatomic world if you built a particle collider like CERN that ringed our galaxy. And you could get up to, you know, magnets all the way around. It would take, it's 150,000 light years across, so the circumference is 2 pi r. So it'd be 600,000 years one way for the first collision to occur. So, yeah. I don't think that's going to happen, right? No. But we could start answering some questions that way. But there's other ways to do it. So gravity and all the forces are just communication between points of space. We can take a look at cosmic rays. These are the highest energy particles coming from mammoth powerful explosions and events out in the universe. And these are traveling across vast distances and going through this fabric of space-time. Well, the way a prism works when you have a little triangle of glass and you beam light in with all these different frequencies, the interaction of the waves with the material, the atoms and molecules that make up the glass, slow down light at a different rate based on the wavelength. And so you get greater or lesser curvature and you get a rainbow out the other side. That same thing is happening in water droplets when sunlight's shining through and give you a rainbow in the sky. So if space-time had a granular nature, you'd expect the high energy light coming from these titanic explosions and events out there to experience some smearing as well. That one frequency would get to you sooner than the other frequency. And right now, it's possible that we've seen a hint in a supernova explosion of some smearing, but more recent results don't see that. I mean, it's right at the edge of what we can detect. And now we have neutrino telescopes. These are looking at ghostly little particles that can zip right through planets and stars, not even really slow down. But we can hopefully start to see, probe the depths of the universe and maybe the Big Bang itself using neutrinos or gravity waves. Since light is doesn't do as well of a job traveling great distances, and light does not make it to us from before the cosmic microwave background portion of the history of the universe. So we're trying. We're trying to use the universe itself as sort of a sensing device for what it's made of. All right, so now we leave the super mathematical and we get into biocentrism. I am not a biocentrist. I think there's a number of fundamental flaws here. What they're basically doing here, and this is a book, Biocentrism by Lanza and Berman, biologist and astronomer. Theory of everything, yeah, not your toe. Sorry, thank you. Is basically taking this quantum weirdness all the way up. The Everett many worlds interpretation of quantum mechanics says that there's one wave function for the universe. How it changes over time is described by what's called Schrodinger's equation. That's all you need. That's the universe happening based on mathematics. They take that similar idea, but they take the Schrodinger cat idea and just start building it all the way up to the universe. That I close the door on Bill, Bill's entangled with the cat. I open the door to see what Bill's doing, but someone closes the door behind me, I'm entangled with Bill, and then maybe out to the people on the sidewalk, and on and on and on until you're talking about distant stars and galaxies getting entangled with what happened with a cat. They just take it all the way up. They say that in a classical story, it breaks, kitty dead, doesn't. What you really have is, in the quantum story, part alive, part dead kitty cat. In the many worlds interpretation, you have the dead cat peeling off in this direction with a live cat peeling off in that direction. What they say is that nothing really exists until it's observed by a conscious observer, whether it's a cat in the box, the inside of a closet over there, or a tree falling in the forest, or the universe itself. In fact, there was a newspaper story out kind of going by this idea that goes off of this idea. This is the cosmic microwave background radiation. This is an observation of the entire sky. This is a real image based on microwaves. It takes a while to stitch it all together, best done by satellites in orbit. And the orange areas are a little teeny fraction of a degree warmer than these dark areas are just a little fraction of a degree colder than the average across the entire sky. This is the last point in time in the universe, all around us, in which the universe is similar to the surface of the sun. You can fly an airplane through the atmosphere of the sun, about 10% down from what looks like a surface. It's about this dense, 10% down. So it's really close to a vacuum at that surface that we see on the sun. It's just so hot that the atoms are still bouncing off each other and the photons can't travel very far. At the surface that we see, it's cooled enough and it's thin enough that the light can just fly free into space, travel 8.5 minutes and get to your eyes and warm you up when you're walking around outside. The universe, this is that baby picture of the universe is when the universe was similar to that. It was still so hot and dense that the photons couldn't travel free. They were still hitting and being reabsorbed and being re-emitted. And then boom, suddenly they got to fly free and travel all the way through the history of the universe until they got to our telescopes to make this picture.
It's residual temperature.
Yeah, you get to see a little,
Only about 3 Kelvin or something.
0.3 or I thought it was really small. Yeah.
Very small.
0.03.
Zero.
Yeah. 0.003, something like that. And so in the biocentric view of the universe, this image really hadn't solidified until we observed it. That it had decohered into all the other possible images that you could get. Maybe a dark spot over here and a hot spot's over here, and maybe a dark spot there, a hot spot there, and every other combination was possible. But when the first telescope looked at the baby universe, that became that image, and now it is. The wave function collapsed. The observation is made. See why I don't like the Copenhagen?
I'm not sure that it's 0.3 degrees. We built a Dewar ball for the Kobe experiment for the Cosmic Background Explorer.
Okay.
And it was cooled with liquid or supercritical helium.
Mhm.
I think we can only get down to about 3 degrees.
Yeah.
And anything colder we can't see, basically.
Well, the temperature of the universe now is 2.73 or something like that. But the difference in temperature is what this is. And I think that's a really small fraction. Yeah. So that kind of bugs me that the universe that we have today got kind of formed that way. You could say that looking out first at our galaxy, then the nearby galaxies, and then we map the structure of galaxies through the universe, started to solidify this image in the biocentric view, because that could only come from a limited number of distributions of warm and cold, or dense and less dense versions of this early universe. But the story in the newspaper was dark matter. Dark matter is a yet to be discovered, hypothesized particle that doesn't interact with light, but it does have mass. And looking at how our galaxy and other galaxies and clusters of galaxies interact gravitationally, there's a lot more of it out there than there is the stuff we see. Maybe up to 10 times more in our galaxy.
The stuff we see is 4 or 5%.
Yeah, 4 or 5%. And it makes up a quarter of the mass of the universe. But we've come up with clever ways by looking at the bending of light of distant galaxies as the light comes towards us. We can computer map, and we usually color purple for some reason, but purple clouds of dark matter. And the story was that because we're now observing this quantum particle that makes up dark matter, that these clouds are becoming more real. And that could spell doom for the local universe.
You're saying the biocentrists wouldn't say that's on the map?
No, the biocentrists say that's what's going on, yeah. Observation causes reality to collapse.
Your observation is not based on direct observation. You just
Right.
described.
But that, they say, is close enough. You now have defined where the clouds are. Now we got two galaxies called the bullet galaxies that have collided and gone through each other. And all the normal matter is now gravitationally warped around, interacted, and you've got this splay of galaxies. But mapping it, you can see the two clouds of their original dark matter, they're just continuing on because they're not interacting through electromagnetism. They're not sticking together. And so we see interesting things going on with dark matter, but the observation in biocentrism says that's firmed it up now. So here there are 7 principles. What we perceive as reality is a process that involves our consciousness. An external reality, if it existed, would be by definition to exist in space, but this is meaningless because space and time are not absolute realities. They're tools of the human and animal mind. Our external and internal perceptions are inextricably intertwined. The behavior of subatomic particles, all particles and objects, are linked to the presence of an observer. Without the presence of a conscious observer, everything diffuses into these probability waves. Without consciousness, matter dwells in an undetermined state of probability, including the universe itself. The structure of the universe is explainable only through biocentrism. The universe is fine-tuned for life, which makes sense because life has observed the universe, and not the other way around. I know it's bizarre, it's backwards from... Time does not have a real existence outside of animal sense perception. Now that's true in quantum physics and general relativity, but there's that entropy thing, and there's processes around black holes that seem to make time just part of the fabric of space and time. Space, like time, is not an object or thing. Space is in the form of animal understanding. It doesn't have an independent reality. What it is and isn't, it implies that you create the reality around you in your mind. It does not imply that you create reality in the universe, kind of a matter like magic. If this was the case, then chaos would ensue because you have more than one observer. As an observer, you force a decision out of the wave function of what you're observing. The problem is there's no persistence of information. I actually wrote Berman an email and asked him about this thing. When you write a book, and I go pick up a book, how do I read the same letters and words that you put down in the book? Because as the book is closed, I mean, maybe worms are eating it, maybe water leaked into it and caused the ink to dissolve, or just quantum mechanically, the pages are all beginning to decohere into a probability wave. And I open up, it collapses, but why isn't it War and Peace, a section of that, or something like that? and he didn't give me a very satisfying answer back. It was kind of hand-waved. But the anthropic principle, the fact that the universe really does seem to be fine-tuned, that there are many different variables that if they were a little bit off, we wouldn't be here to observe it. So does that, they take it backwards and say that the universe is tuned for life because we became conscious of it. Right?
What is life?
No. Well, you can make the argument that fire is life. It's got a lot of the same properties of life. It doesn't seem to think, but that, neither do bacteria that we know. Viruses, are they alive? Yeah. We'll play it with that actually in the next section when we get into exobiology and things like that. Question from Martin, was it Baudrillard? If the wave function of the early universe was decoherent, so this picture was all fuzzy until we observed it, it would have interacted with matter energy differently, making different patterns in cosmic microwave background radiation. But does this go to quantum erasure? That idea that the light's going through the slit and then it creates the interference pattern unless I observe it. Then I don't get the interference pattern. But if I erase the answer, so if we took a picture of the early universe and deleted it, the universe stay fuzzy all the way back? There's a similar problem, and there's actually an experiment that's being used in quantum encryption about this, because we have gravity acts like a lens. And so big galaxies out in the universe are bending space-time around it. And when you have very distant galaxies or quasars, galaxies in the early universe that have active black holes in the center, putting out lots of extra light, there are special cases that Einstein predicted where the light would come through in 4 points around the nearby galaxy from our point of view. And that's called an Einstein cross, or make a ring. You get an Einstein ring. Or just you get an image of the distant galaxy magnified or distorted, because it's kind of random how this lens of space-time is warped. But in the special cases where you get like a cross or two images of the galaxy on either side of the galaxy, you have the double slit experiment going on the galactic scale. You've got light that's coming from this galaxy. It's making a decision to go right or left around a whole galaxy, and both pathways are traveling all the way to you on Earth. And so you can work to make an interference pattern from those two, just like our little bitty lab tabletop experiment, and you can choose to play around with it in the same way you would a local experiment. But the weird thing is, you're talking millions or billions of years of time that the light has been in travel, that you get to play with it somehow. But they're working on trying to encrypt information that way by looking at galaxies being warped that way, or the light of quasars on opposite sides of the sky, and then putting that into a computer system to make it so you can't get the information back out unless...
Usually referred to as lensing.
Lensing, right. Yep. So the question is, do we observe the universe now, and that made the universe basically go through the slit that it went through at its creation? That it could have done all these different things with or without life, but it went this way now because we've observed it. It makes my head ache. I'm not really happy with biocentrism, but it pushes an extreme, and maybe it's good to think about because it shows how it breaks.
Yep.
And the many worlds interpretation solves that by saying the observer isn't important. It all just branches off. Everything happens. You're just traveling your pathway down through the decisions. So again, I'm becoming an Everettian, so you don't get the Schrodinger's cat up to the universe size. So can we even get a final theory? That's a good question to ask. Bertrand Russell, who lived up to 1970, put out the Principles of Mathematics in 1903. David Hilbert proposed that mathematics needed to state all the axioms of mathematics. That way we can get rid of any mathematical paradoxes and inconsistencies. So this is similar to what we were talking about. Does mathematics exist and you're just discovering it, or is it something that we create? But he wanted to create all mathematics into just a set of everything that is possible and be finished. Write the final book of math. That way mathematics would be formal, complete, consistent, conservative, and decidable.
And it's a great way to kill it all. It's a great way to kill it all.
It would kill, yeah, it would put all the mathematicians out of work. Well, along came Gödel, and Gödel dropped a bomb on this goal of creating the final book of mathematics. He was a logistician, a mathematician, and a philosopher. He published his theorems in 1931, so it didn't come too long after this goal was set. And what he said is that any effectively generated theory capable of expressing elementary arithmetic cannot be both consistent and complete. That's their goal. They wanted it consistent, complete, and done. And he proves that there are true statements that are unprovable within just arithmetic. You don't have to get to anything heavy that has addition, subtraction, multiplication, division. You're doomed. And there are not a finite number of axioms. You can't really write the final book of mathematics. Just to define, an axiom is a proposition that cannot be proven. It's self-evident building block of mathematics or logic.
Observation.
Yes.
To go to these last couple mathematicians.
Mm-hmm.
It's very interesting that they're all published in their 20s or 30s.
Mm-hmm.
Just looking
Very
at his
early
age.
in life.
I'm just looking at his age.
Before they really have the gravitas and maybe the depth.
Mm-hmm.
That when you grow older, you get a little wiser sometimes, and you think about it a little more.
They're upstarts.
Yes.
Well, I think in the mathematics world, common wisdom is by the time you're 25 or 30, you're done.
Yes.
You're not going to make a earth-shaking contribution.
This time, the same thing, basically.
Yeah, when you're young and your
Do
brain,
much later on in life.
yeah, and you can solve additional problems, you can flesh out work, you can, yeah.
But the great idea, the breakthroughs.
The big breakthroughs seem to come from young people. One exception is, let's see if my brain will produce the name of it, Fermat's last theorem. Is, let's see if you have x squared plus y squared equals z squared, you can solve that. That's just Pythagorean's theorem. But if you change it to x cubed plus y cubed plus z cubed, or x to the fifth plus y to the fifth equals z to the fifth, Fermat said there is no solution to those, ever. He said he did it in the margin of a book, and he was happy. Well, the book got lost, so there was nobody ever had that proof. We just had this claim from this great mathematician. It was pretty trivial for him to prove that. People have spent centuries working on that, and finally a guy in his 50s or 60s, I don't remember his name, sorry, did prove it. It was a Herculean effort. It was hundreds of pages of proof. He had to go back and fix some flaws in it, but still held together. It's one of the greatest modern achievements in mathematics. He did that in his later life. But it was just this brute force determination. It's like it took over his life. His wife was very patient with him. I think he even created a silent room in his house that he would just go in for hours a day and work. And yeah, there's a whole book on it, Fermat's last theorem. It's really fun. But yeah, for the most part, it seems that the big breakthroughs are a young person's world. So what Gödel did is basically this. He used prime numbers to map these axioms and theorems to show logically true statements that can be proven. And this is very similar to this. I say this statement is false. Okay, is that true or not? Well, if it's true, then it's false. If it's false, then it's true. If it's true, it's false. If it's true, I'm caught now. He had a second theorem that any theory including complexity equal to the arithmetical truths or containing them, theory can only include statements of its own consistency. So I can say, John cannot say that this statement is false. All right, you guys can answer that, but I can't, because you're outside observers. So kind of mind twisting. So he uses this concept of self-reference, that the ability for the mathematics to look back on itself and make a statement about itself is what's critical. And in a way that takes us back to an observer mathematically again. So it's kind of creepy. In fact, looking at self-awareness or consciousness, it seems to be an important ingredient that distinguishes us from the consciousness of a cat or a dog. As far as we know, cats and dogs don't think about themselves thinking about themselves, or think about themselves thinking about themselves thinking about themselves. But it's something we can do as deep as we want to go. I can self-reference my own thinking process and thinking about my thinking process. You are in a trap, but at the same time you can get out of it by just stepping aside. That's another part of the flexibility of human conscious thought. Now, that's the only one I can experience.
That's not an elegant mathematical solution.
No, but that's called a meta-mathematical statement. And Hofstadter, what's his first name?
Gert
Gödel. No, not Gödel. Kurt. Kurt. Is that right? No, Kurt. Oh gosh, it's gone. The book is called Gödel, Escher, and Bach by Hofstadter, written in the 80s. And it goes in unbelievable detail working on how the music of Bach, the thinking process of Gödel's incompleteness there, and the concept of an Escher painting where the staircase meets back on itself, or a hand is drawing itself on this while it's drawing itself. And that ability to curve back in is really critical to a lot of reality. And so I've been reading that book since the 80s. I'm still not done. My daughter is scandalized by it. How long have you been reading this, Dad? Since before I was born? Yeah, but I'll get to a section and then I'll have to hop off and start pulling in other books related to that, or the mathematics of set theory. And so it's becoming my life quest to finish this dumb thing. So the question we're asking is, in a universe in which basic physics seems very much to incorporate at least arithmetic, if not all the heavier mathematics, there may be no end to the discoveries one can make or the statements one can make about reality. If mathematics and the real world are so linked, then Gödel's incompleteness theory, the idea that there's no final set of axioms, might apply to the universe. But is it possible that all this complex math that we're using in the universe is not needed? Is it possible that the universe is built on something simpler, maybe just addition and subtraction, and maybe it is possible to eventually strip out all the higher craziness and get really down to it? And can the human mind serve as sort of an outside system that can answer the question? John cannot say if this statement is false or not about the universe. And one approach comes from mathematician Stephen Wolfram, famous for a software package that is like a universal mathematical tool or environment that his company created. Very similar to the guy working on Fermat's theorem. When he was working on his book, oh come on, where's his book? It's called, oh jeez. The concept of cellular automata, but the book is a new kind of physics. Is that what it is? I might be the subtitle of it. It'll come to me. He worked on this idea of cellular automata when computers were really new. I mean, he had like 286s and 386s to work on. He created a soundproof room in the middle of his house also, and went in there with these brand new computer devices and worked on basically setting up really simple rules. He'd start with a single black dot, and he'd have a simple rule to say if there's a black dot, then on the right, in the next step, you put a white dot and a black dot, white dot, black dot, white dot, black dot. And then on the next step, you do that again. So now a white dot, a black dot becomes two whites and a black, and just you keep repeating step after step a very simple rule like that. We're not using high mathematics at all. And the game of life is similar to this, where you start with a seed point. You have very simple rules. Just for each point, each step forward, you say, if this exists, then the next step you draw this pattern around a pixel. And it doesn't take very many little rules like that to create weird things like this. So here you got two seed points. The two seed points seem to make this oscillating blobs that move towards each other and back, and they keep spawning these little dots that move down. And the rules are really simple. Or here's one in which you have these little critters. You get rules that not only define what gets drawn next, but what color they change. Well, the color they change and where they are makes the next step. And you've got spinning things here, an oscillating thing here, but it's something that's like warbling back and forth. That is complexity. That seems to be structure emerging out of almost nothing. Here you're getting a pattern down time that is pretty boring on this side, You just got these stripes of patterns, but over here, you've got cells and opening that almost look, well, they look random. Kind of like the beginning of the universe with the cosmic microwave background radiation pattern. Alan Turing came along, 12 to 54. He proved in 36 a general algorithm to answer the question, will this program ever finish and give an answer? And he showed that that's impossible for any program that comes along. So if Windows locks up on you and gives you a blue screen of death, it's Turing's fault. This is called the halting problem. It's very similar when you get down to the mathematics of Gödel's first theorem. That when you have reality being generated in a programmed way, or in a way like this, you can't state whether you're going to get a final answer or whether the program is going to ever stop with an answer. If the universe is computational in nature, that may apply to this reality around us as well, going back to the holographic principle. In this framework, there's no resource limitation, so there's no limit on the amount of memory or time required for a program to execute. You have as much storage as you want to let it keep running. So kind of putting Gödel and Turing together, suppose that the universe we live in is in fact a simulation, or at least acts like one. It's being simulated by the equivalent of a Turing machine. What are the ramifications of the halting problem and Gödel's incompleteness theorem in this regard? And so it kind of makes it seem like we could be living in the Matrix. You ever seen the movie The Matrix? I don't want to spoil it. I went into seeing The Matrix when it was in its first run. No idea what the film was about. And it has a big twist about a third of the way in that...
Never heard the twist either.
Okay. Do you want me to spoil it for you?
Sure.
Okay. Spoiler alert for the people watching the video here. All right, so you got a guy going through life. He doesn't like his life, but he has a feeling there's something deeper in reality than it seems. And he is reaching out on this fledgling internet. I think this came out in the late 90s, so the internet was brand new, even then, to the real movie creators.
So still aren't unlimited then, right?
Maybe. Yeah, the internet kind of went commercial about 96. I think the movie came out in 99, 97, something. We're about to get another Matrix, fourth one out. And so someone challenges him anonymously on the internet named Morpheus that if he wants to know the nature of reality, come meet him in a certain time or place. And he has some government-like agents try to stop him, and he doesn't know why that's happening. But eventually he meets Morpheus in a room, and Morpheus says you can take the blue pill, go back to your life, forget this ever happened, take the red pill and follow the rabbit hole down as far as it goes. So he takes the red pill, and the world around him just starts freaking out and warping, and then a blast of special effects occurs, and he is completely naked, hooked up to hoses in a vat of goo, and he stands up and can't breathe, and he pulls this thing out, and he's in this futuristic world with machines tending to sleeping humans in vats. And everything that he's experienced is a simulation in his brain fed by this master computer, and they're using humans in the distant future for other reasons. And the movie goes from there. I just got chills. Goes from there and how he deals with it, and all sorts of stuff happens over the next two movies, and now a fourth movie coming. Yeah, there's two more. The first one by far is the best. Second one is rough. The third one kind of got its footing under a little bit better, but people are hoping he's sort of a messiah-like figure that will be able to go back in the Matrix and get the rest of humanity liberated. So if we were in such a simulation in some way, what could we look for? Are there ways to see through this? Well, we might see software glitches. Do we see errors happening around us? In the Matrix, they said that sense of deja vu that we get, that glitch that we've done something before, is like because everything did stop and just restart for a moment to fix something. A master program is monitoring flaws and rebooting. Yeah, maybe a moment of deja vu is something in which the entire system was offline for a few years before it got restarted again right where it left off. Who knows? Easter eggs. Let's say it's not accidental I'm sorry, it's not purposely not accidentally a nature of reality, but actually there's some higher intelligence out there that built the reality around us. Are there programmers out there who are leaving messages for the smartest of us to decode? So maybe way out in the digits of pi or e, there's some simple messages like, hi, we're out here, or something for us to discover someday. Problem is, the digits of beyond the decimal point in pi and e are infinite, so everything is actually out there. Every book ever written, every DNA strand is encoded someplace in pi between here and the infinite end of the digits. So it's not a great way to leave a message. Our limitations on processing power. So maybe if we go way down to the fine scale of space and time, we find granularity, but the experiments try to erase these. Maybe the Heisenberg uncertainty principle, that those virtual particles that we see in physics are maybe part of the program running, that you're seeing the ones and zeros in a physical way that way. So anyways, it's kind of weird. There's I don't have it up here, I thought I did. I have a test myself that we could do, that when, you know what a zip file is? Okay, so a zip file compresses a file. It takes out extra space, it takes out redundant strings of ones or zeros or something, and it says, instead of writing 30 zeros in a row, it just says, here, put 30 zeros, which takes a lot less space. What happens when you try to zip a zip file? You don't, nothing happens. It's still the same size. It's already done the compression that it can do. So if we could find a compression, let's say I'm using styrofoam balls or atoms, and I'm trying to find different arrangements for these things. If the universe uses some form of compression to save space and to make computation simpler, then if we try to compress it in this reality again, it won't compress when it should. So if we find a compression algorithm for stuff that should work, but it doesn't, that would be a hint that we're living in a simulation that uses that kind of compression. Who knows? So summing up, string theory is the most researched, has addressed many of the disconnects between quantum mechanics and general relativity, but it doesn't have a lot of testable predictions that we can get to right now. It doesn't create its own space and time. So even if it's the front runner, there's a lot of work still to be done on it. Loop quantum gravity is less popular, but it does hint at things that could be tested. It creates its own space and time. And recent findings links it in string theory through this holographic principle. So that's hopeful that those two are going in the right direct way. Biocentrism is a bold step that ignores the many worlds interpretation, takes the Copenhagen interpretation to an extreme, but it relies on consciousness. And I'm going to do this presentation later this year up in Estes Park, but I've written a book on reality. It's actually at the publishers, and last week I got the publication offer. So I have an offer for this book to be published. I'll probably sign it this week. I'll probably go for it. But one of the observations I make is, there's also a big section on theology in there too, that when you make the human position important in a physical theory, you're probably wrong. Going back to the geocentric universe of the pre-Copernican time with the sun and the heavens all rotating around the earth in the middle of the universe. That was wrong, but that's our natural inclination. We like to put ourselves in the middle of everything. So biocentrism is like the ultimate sin of this, saying that the universe itself exists because great old humans observed it. Theologically, I say the same thing. If you make a theological claim where humans are the center of everything, that we're the, yay, let's go, the world needs humans, that's not true either. So anyways, that's in my book, and I'll talk about that in a future thing. In the computational universe, we might live in a universe that acts like a calculated simulation based on information. Most likely it acts that way than it really is. I'm not ready to say that we live in a simulation. I don't see anything around us that really indicates that. But maybe the most amazing thing is not if we can find a theory of everything, it's that the universe can be explained as much as it has already. But that's pretty neat. So a whole bunch of references here. I don't know how many of you you're interested in pursuing, but also Astronomy Magazine, Sky and Telescope, a lot of those things help get onto these topics. So the next section we get into is a whole new slide set. We're going to do life, the universe, exoplanets, search for extraterrestrial intelligence, UFOs, space and time travel, and careers in this, doing this stuff.
Could you go back to the one, sorry, the next one? Okay. So the magazine title.
All right. So that's perfect stop. We made it almost 2 hours. And we finally quit painting over the same material.
You have to get out of here, why don't you stop it?
Yeah, I will.
I'll clean up and I'll move the data off the chips
Okay.
onto the hard drive here.
Okay. Wish I could take the chips with me, because maybe I will be able to get to editing.
Okay, take the
But-
chips with you and
well-
then drop them back off your.
Nah, you better back them up though. Yeah, okay, I'll do that.
15th is the next start line, so,
Okay.
which is not that far away, it feels like.
And so the topics you just mentioned for the future is going to be next month?
That's where we start next month. Yeah, we'll start.
How we go.
Okay, that'll be the last one. I'll be here for a while.
Okay. Well, you've been through the thickest. This is
It's easier from here?
you're at the culmination of a lot of background. But hopefully I helped link it all together for you.